Hello everyone, welcome back to class 6 series on my channel Mathify with Meenakshi. In the previous video, we explored factors, multiples and learned how to find prime numbers using the method sieve of Eratosthenes. Today we will practice some questions based on these concepts. So let's move to figure it out. That's on page number 114 of your textbook Ganita Prakash. So let's see question number 1. We see that 2 is a prime and also an even number. Is there any other even number? So let's write its solution. You know that no, there is only even prime number is 2. So I will write this. No, there is no even prime number except 2. As if it's even, then it's one of the factors is always 2. So this is the reason why we can say that 2 is the only even prime number. Now let's move to question number 2. Look at the list of primes till 100. What is the smallest difference between two successive primes and what is the largest difference? So I have attached this pic for you so that you can see the prime numbers easily. You know the circle numbers are prime numbers. So first thing we have to tell that the smallest difference between two successive primes. So just see where we have the least difference. Here we have the least difference and that's 1. 3 minus 2, that's 1. And where is the largest difference between two successive primes? So if you will see carefully, here the difference is 2, here the difference is 2, then the difference is 11 minus 7, then 13 minus 11, then 17 minus 13. So the largest difference is here, 97 minus 89. So I will write the largest difference is 97 minus 89, that is 8. So answer is 1 and 8. Now let's move to question number 3. Are there an equal number of primes occurring in every row in the table on the previous page? So I have already attached the pic for you, so no need to see the previous page. Which decade have the least number of primes and which have the most number of primes? So here first, they are saying that can we say that they have equal number of primes? No. You can see here, like in first decade, this is first decade, we have 4 primes. In second decade, again we have 4 primes. In third decade, we have 2 primes. Then in fourth decade, we have 2 primes. Then in fifth decade, we have 3 primes. Then in sixth decade, we have 2 prime. Then seventh, 2 prime. In eighth decade, 3 prime. And in ninth decade, 2 prime. And in 10th decade, only 1 prime. So I've written the number of decade here. So they are saying we have equal number of primes. So that's no. You will write no. We don't have equal number of primes in each row, or you can say in decade. Now they are saying which decade has the least number of primes and which have most. So as you can see here, the least is for the last decade, that's 10th. Only one prime number is there. So we'll write the 10th decade, that is 91 to 100, has the least number of prime. As you can see that we have only one prime, that is only 1. And what is that? 97. We have only one prime number, that is 97. And where we have the most number of primes, that you can see in first and second decade, we have 4 primes. So we'll write first and second decade, that is 1 to 10 and 11 to 20. I'm writing the decade too in case you get confused. Has the most number of primes, as each decade has 4 primes. 4 primes, and what are they? In first decade 2, 3, 5, 7, and in next decade 11, 13, 17 and 19. So answer is here first and second, and we have 4 prime numbers. Let's move to next question. Question number 4. Which of the following numbers are prime? 23, 51, 37, 26. Although you should know that prime numbers are those numbers that have only two factors, 1 and the number itself. So 23 is a prime? Yes. 51, no, you can see 5 plus 1 is 6, so it is divisible by 3. 3 into 17 is 51. 37 is prime, yes. Here I will write no because it is divisible by 3 and 17 too. And 26 is an even number, so you should know that 2 is the only even prime number. So again here it's no. So answer is only 23 and 37 are prime numbers. Even you can see this table. I have attached the table for you. Now let's move to question number 5. Write 3 pairs of prime numbers less than 20. So we have to write 3 pairs. So I'm writing boxes. One pair, second pair, and third pair. 3 pairs whose sum is a multiple of 5. Whose sum is multiple of 5. So sum can be 5, 10, 15, 25, anything. So I'm taking 5, 10, and 15. The condition is that these two should be prime numbers. Okay, let's take how I can write 5, 2 plus 3. How I can write 10, 3 plus 7. How I can write 15, 2 plus 13. So you can even write 20 like 7 plus 13, but they said that you have to only write 3 pairs, so I have written these 3 pairs. Now let's move to question number 6. The numbers 13 and 31 are prime numbers. They are saying when you will reverse the numbers, like 13 is a prime number, and when you will reverse it, again it's a prime number. So you have to find such pair of prime numbers up to 100 from this table. So let's see. First I will tell you how you can see, like if you take 13, 31 is given. Now 17, if you will reverse 17, you get 71. Yes, it is also prime. So you can write 17 and 71. Then if you know 19 is a prime number but 91 is not, so we can't write this. 23 is a prime but 32 is not. 29 is prime but 92 is not. 31 is prime, that's already given. 31 and 13, it's given in example. 37 is prime and 73 too. So you can write 37 and 73. Then 41 is prime but not 14. 43 is prime but not 34. 59 is prime but not 95. 61 is prime but not 16. 67 is prime but not 76. 71 we have already taken. 73 is prime and 37 that we have already taken. 79 is prime and 97 too. Then 83 is prime but 38 is not. 89 is prime but 98 is not, and 79, 97 we have taken. So only these 3 pairs are possible whose reverse is also prime. They are saying up to 100 you have to write. So we are writing only up to 100. So 3 pairs we have written. Now let's move to question number 7. Find 7 consecutive composite numbers between 1 and 100. So you have to write 7 numbers that should be consecutive and they are composite. Just see here where we have 7 composite number. In first question we have seen that the largest difference between two prime numbers is here 97 and 89, and if you will see 7 composite, 1, 2, 3, 4, 5, 6, 7. So we have 7 composite numbers between 89 and 97. That is 90, 91, 92, 93, 94, 95, and 96. If you will see any other case, then it's not possible that you have 7 composite numbers between 1 and 100. You will always find one prime number in between. Now let's move to question number 8. Twin primes. First, they are telling you the definition of twin primes, that they are the pairs of primes. This is very important, that in twin primes, both the numbers should be primes. And there is one more condition, that difference between those primes should be 2. So if you can find two prime numbers whose difference is 2, you can say they are twin primes. One example they have given you 17, 19, and one example they have given you 3, 5. So you have to find other twin primes. So let's try to find here. 3, 5 they have given you. So we can write 5, 7. One is 5 and 7. Then next you can see 11 and 13. Then next 17, 19 they have already given you. Then we can write 41, 43. Whose difference is 2? Basically we have to write those prime numbers. Then we can write 59 and 61. Difference is 2. Then 71 and 73. And one we missed, 29 and 31. So these are the 6 twin primes other than 17, 19 and 3, 5, because these two pairs are already given. Let's move to question number 9. Identify whether each statement is true or false. Explain. That means you have to give reason. So A part, there is no prime number whose unit digit is 4. So yes, we know that if a number ends with 4, then it's a even, and we have only even prime number, that's 2. So this is true. There is no prime number whose unit digit is 4. As if a number ends with 4, then it is always divisible by 2. And if it is divisible by 2, you know that it is no more a prime, because a prime number only divisible by itself and 1. So I've written the reason too. Now, a product of primes can also be prime. No, because it's a definition of composite number. False. Product of prime numbers is always a composite number. I will give you example too. Example. If you will say two prime numbers, let's say 2 into 3. Then what is 2 into 3? It is 6. Now you know that means 6 is divisible by 2 and 6 is divisible by 3. And you know the definition of prime number, that it is divisible by only 1 and the number itself, that is 1 and 6. But that is wrong, because if you are writing any number as a product of two numbers, then that means those numbers are the factors of that number. So that's why it's false. Now let's move to C part. Prime numbers do not have any factors. No, they have two factors. So again it is false, as prime numbers have two factors, one and the number itself. Now let's move to D part. All even numbers are composite numbers. Now this is also false, because you know that there is one even prime number, that is 2, as 2 is the only even prime number. Now let's move to E part. 2 is prime and so is the next number 3. For every other prime, the next number is composite. Yes, it's true. Because you know that if they are saying that every other number, that means one is even, one is odd. Yes. And you know that only even prime number is 2. Is 2. So we have only one possibility, that is 2 and 3. I can say here also we have odd then. So only 2 and 3 can be the possibility that are next to each other, and one is prime, one is composite. But for rest, you know that if any number is prime, then it should be odd, and the next number is even, and that can't be prime number. So that is true. I will write the same reason, as for every other prime, the next number is composite. And I explain you the reason too, because all the prime numbers other than 2 are odd, and the next number is even, and that is always composite. Now question number 10. Which of the following numbers is the product of exactly 3? This is very important, that we need only exactly 3 numbers and they should be distinct. So let's do this. How we'll do this? We'll take the prime factorization. First take the prime factorization of 45. As you know that sum of digits is 9, so it's always divisible by 3. 3 into 15, then again 3 into 5, and then 5 into 1. So here you can write that 45 is 3 into 3 into 5. So here we have two distinct prime numbers, but they are saying we need exactly 3. So let's move to next part, 60. For 60, you can divide by 2 because the last digit is even, 30. Then again you can divide by 2. This half is 15. Then you can divide by 3. 3 into 5 is 15, and then 5 into 1 is 5. Again, what is 60? 60 is 2 into 2 into 3 into 5. Now here you will write that it's a 3 distinct prime, but not exactly, because 2 is coming 2 times. So 3 distinct prime numbers, but 2 is coming 2 times. That you will mention here. 2 is coming 2 times. Now let's move to 91. As 91, just see here that 91 is divisible by, you know 91 is divisible by 7, as 7 ones are 7, and then 13, and then 13 ones are. So here 91 is 7 into 13, that means here we have two distinct prime numbers. Next is 105. As you know that sum is 6 here, sum of digits, so we can divide by 3. 3 into 3 is 9, and then 1 left, 15 is 5. Now again you can divide by 5, 5 into 7 and then 7 into 1. So 105 is equal to 3 into 5 into 7. So here we can say that it's exactly 3 distinct primes here. Exactly 3 distinct primes because no number is repeating here. Exactly 3 distinct primes. Now let's move to last part, that's 330. As you can see, again the sum of digit is 6, so we can divide by 3. 3 into 1, 3 into 1 and then 0. Now as it ends with 0, so you can divide by 2. Just take half, 55. Then you can divide by 5, it's 11, and then you can divide by 11. So here we have 4 distinct primes. 330 is equal to 3 into 2 into 5 into 11. But what we have to find? They are saying that you have to write exactly 3 distinct prime numbers. So answer is 105. Now let's move to next question. Question 11. How many 3-digit prime numbers can you make using each of 2, 4 and 5 ones? You have to use each digit once and you have to write 3-digit number and you have to tell how many prime numbers can be possible using these 3 digits. Now you know that either it can end with 2 or it can end with 4 or it can end with 5 because we have only 3 digits 2, 4 and 5. So if it end with 2, that it means it's even number and then it's always divisible by 2. And you know that prime number is divisible by only 1 and the number itself. So that means it's not possible that a number end with 2. If a number end with 4, again the number is even. That means it is divisible by 2. And again it is not a prime number because prime number is divisible by only 1 and the number itself. And if it's end with 5, then it is divisible by 5. Again it's not a prime number because prime number is divisible by only 1 and the number itself. So that's why we can say that there is no 3-digit prime number that we can make using the digits 2, 4 and 5 using them once. So I will rub that and I will write the reason now. There is no 3-digit number. There is no 3-digit prime number that can be made using the digits using each digit 2, 4 and 5 once. And why is it so? As if unit digit is 2 or 4, then it is always divisible by 2 because it's an even number then. And if unit digit is 5, then it always divisible by 5. And that's why it's not possible. Let's move to question number 12. Observe that 3 is a prime number and 2 into 3 plus 1 is 7. That is also a prime number. Are there other primes for which doubling and adding 1 gives another prime? Find at least 5 such examples. So we have to write 5 examples such a way that if you will double a number and you will add 1, the answer is again a prime number. So where I'm using boxes, that should be filled by prime numbers. So here also you have to write all primes and here also you have to write all primes. So let's think first. So what I can write like 2 into 5. You can't write 3 because they have already given you as example 3 and 7. So 2 into 5 is 10. 10 plus 1 is 11. Again prime. Now think for the next prime number, that is 7. 2 into 7, 14 plus 1 is 15. So you can't write that. Then 2 into 11 is 22 plus 1, 23. Then 2 into 13 you can't write because that is 26 plus 1, 27 is not prime. So you will write like this. So even I can write 2. 2 into 2 is 4 plus 1, 5 is a prime number. You can write 2 into 23, 46 plus 1, that's 47 is again a prime number. And you can write 59 is prime, so how you can get that? 2 into 29 plus 1. 59 is also a prime number. Now let's move to page number 115. That's not a figure it out. It's normal question that's given on page number 115. Question number 1. Where should Grumpy place the treasure so that Jumpy cannot reach both the treasure? You know that when Jumpy can reach to both the treasure, when he will find the common factor of both the treasures. But this time they are saying that where should Grumpy place the treasure so that Jumpy cannot reach both the treasure. So you should know what Grumpy can do. Grumpy can select safe pairs. And what are safe pairs? If the pairs don't have any common factors. Pairs don't have any common factor. And we know that if the pair don't have any common factor other than 1, because we know that they always have 1 as a common factor, and that is not allowed. They said the jump size of 1 is not allowed. So that means Grumpy have to select co-prime numbers. If Grumpy will select co-prime numbers, then Jumpy cannot reach to both the treasure using the same jump size. So now they are asking if these pairs are safe, that means the numbers are co-prime or not. First, 15 and 39. You know that 15 factors are 1, 3, 5 and 15. And factors of 39 are 1, 39, 3 and 13. So they have any common factor other than 1? No need to see 1. Other than 1? No. So that means yes, it's a safe pair because they are co-prime. Safe pair. Now let's move to second. 4 and 15. Again, what are the factors of 4? 1, 2, 4 and 15. 1, 3, 5, 15. Again, there is no common factor other than 1. So again, they are co-prime. That means it's a safe pair. Let's move to see 18 and 29. Again, 18 factors of 18 are 1 and 18, 3 and 6, 2 and 9. And for 29, it's a prime number, only 1 and 29. Again, it's a co-prime. It's a safe pair. Let's move to last 20 and 55. So what are the factors of 20? 120, 210, 4, 5. And what are the factors of 55? You can say 1 into 55 and 5 into 11. So here we have 1 as common factor as well as 5. So this is not a safe pair because they are not co-prime. If here Jumpy will select a jump size as 5, so he can reach to both the treasures. That means it's not a safe pair for Grumpy. Now let's move to next question, and that's on page number 116. Again, it's not a figure it out, it's normal question on page number 116. Which of the following pair of numbers are co-prime? So in previous page they asked indirectly, but here they asked directly by saying the word co-prime. So again you will do the same process. That what are the factors of 18? You know that 1 into 18, then 2 into 9 and then 3 into 6. So all are the factors. And for 35 it's 1 into 35 and 5 into 7. So only 1 is a common factor here. So I can say that they are co-prime. For 15 and 37 again the factors are 115 and 35. And for 37 it's a prime number, so 1 and 37. Again they are co-prime. Let's move to 30 and 415. For 30 you can write 1 and 30, 2 into 15 and 3 into 10 and 5 into 6. So these all are the factors. And for 415 you know that it is divisible by 5. So 5 into 83 and 1 is 1 into 415. So here the common factors are 1 and 5. So you can say that the numbers are not co-prime. Even you can see that one number is end with 0 and one number ends with 5. So 5 is a common factor here. Directly also you can see in case it will come in MCQ. Now 17 is a prime number, so only 1 and 17. And for 69 it's 1 into 69 and you can say 3 into 23. So here we have 4 factors, but again they are co-prime because only one common factor is there, that's 1. Now let's move to last part, 81 and 18. Again you can write that 1 into 81, 3 into 27 and 9 into 19. So you will write 9 only one time. And here 1 into 18 and 2 into 9 and 3 into 6. So common factors are 1, 3, 9. So that means again they are not co-prime. Because for co-prime, the common factor should always only 1. Only one common factor, and that is 1. Now let's move to next question. While playing the Idli Vada game with different number pairs, Anshu observed something interesting. Sometimes the first common multiple was the same as the product of numbers, and at other times the first common multiple was less than the product of two numbers. Find examples for each of the above. How is this related to the number being co-prime? So what we'll do here, I will just tell you what was the idli vada game. Suppose it was the multiple of some number, like multiple of 3, and vada was multiple of 5. Then first time we'll say idli vada is the first common multiple of both the numbers. You can say LCM of 3 and 5. And in that case it was 15 because both the numbers were co-prime. So that was the question. Sometimes the first common multiple, that's the LCM, was the same as the product of two numbers, like in our case 3 and 5. So can you see when it will happen? Yes, when the numbers are co-prime. Whenever the numbers are co-prime, the least common multiple is always the product of numbers. So you will write it's true when the numbers are co-prime. Example 1, I have already given you 3, 5. You can say 2, 3. You know that when the numbers are co-prime, when you will take consecutive numbers, when you will take both the prime numbers, or when you will take any two numbers whose common factor is 1, like 4 and 9. Now let's move to second case. They are saying at other times the first common multiple was less than the product. This time LCM is less than product of numbers. So when this will happen? When the numbers are not co-prime. It's true when the numbers are not co-prime. So I will give the example of that too. Example 2 and 4. Here the first common multiple, that means the LCM, is 4, and that is less than product because product was 8. Yes, this is product. Similarly, I will give you one more example. 6 and 9. Again, the first common multiple, I can even write LCM of 6 and 9 is 18, and again that is less than product 54. So whenever the numbers are co-prime, the first common multiple is always the product of numbers, and whenever the first common multiple is less than product, that means the numbers are not co-prime. So you should know this thing. That's it for today. Now we'll continue this chapter in next video. If you found this video helpful, don't forget to like, share and subscribe to my channel Mathify with Meenakshi. Thank you everyone.